Hello, I would like to welcome you to the first lecture of 3N03. I will try to cover in this lecture some of the basic concepts we need in electricity. We'll talk about the Bohr model for the atoms, which will give rise to discussion about insulators, conductors, and semiconductors. One other important thing that even some electrical engineers do not think about that much is how the currents that we have in circuits are related to electric fields and so on. So I will start by talking about electric forces, and then we'll talk about electric fields, and then we'll talk about the potential, the current, and the voltage drop. And we'll see how we can take these concepts from basic charges to actual circuit elements like resistors and capacitors and so on. One of the models used to try to model an atom of a general material is the Bohr model. And the Bohr model is simply a visual model of the atom. It shows the nucleus that you have. So you have a nucleus here, and this nucleus contains the protons, the positive charges, and the neutrons. And these are neutral charges. They are all at the center of the atom. So the atom is really represented by a sphere. And then the electrons do exist around the atom in a number of orbits. So this is one orbit here, and there is second orbit here, and so on. And every orbit can accommodate certain number of electrons. And the further the electrons are from the nucleus, the more the energy is. So the electrons in the outermost orbit will have more energy than the ones, say, in the very inside. So this is called the Bohr model, and it's used to describe how the different materials are structured and so on. There is something called the atomic number. Atomic number of an atom is simply the number of positive charges or positive protons in the nucleus, and it's also the number of all the electrons in the orbits. Remember, the atom is electrically neutral, so the number of positive charges is equal to number of negative charges. We call the electrons in the outermost orbit or outermost shell, we call it the valence electrons. And these are sometimes in some materials these are free for conduction. They can leave the atom, and then we can use them to create current. And these are, in that case, become conduction electrons. So just remember that the outermost orbit or outermost shell, we call it the valence shell, and the electrons in this shell are called the valence electrons. Conductors are very important for us in this course because many of the resistors that we are going to be using they do conduct current. They allow some current to go through them with different degrees, of course. So materials that can allow current electrons to move to some either significant amount of electrons or limited amount of electrons, we can classify them as conductors. I'm showing you here the color or the shape for this atom here. This is the copper atom, and the copper atom, it has an atomic number of 29. So there are 29 positive protons at the center, and there are 29 electrons distributed over a number of shells. And the outermost shell contains only one electron, and this electron is really lightly tied to the core. We call all the nucleus and all the other electrons around it, other than the one in the outer shell, we call it the core. So this is the core of the copper atom. So this electron here, which is in the outermost valence shell, is really not tightly connected to the atom, and if it has sufficient thermal energy, or if you apply an external electric field, it can start to drift. So it can start to leave this atom and start to conduct. Once you have electrons moving, then you have current, and this is you can use this one to create resistors and all type of other material or wires, and whatever the case may be. So let's keep in our mind that conductors are materials that they have their outermost electrons. They are not tightly connected to the atom, and they can leave very easily if they are given enough thermal energy very little thermal energy maybe, or even without any thermal energy. They can simply leave the atom and then conduct current. And if you apply electric field, as I will explain to you later, electric field will make electrons drift against its direction. So this results in a current in the direction of the electric field. I will explain this in the later slides. A second type of material that we'll be using here in this course is insulators. And these insulators, we have them very often in cables and so on. So this is a typical cable here. You can see you have a number of wires, 1, 2, and 3 wires, and each one of them has its own insulation. This insulation, it's usually they are compound materials, they are like glass, they are rubber of some sort. They have their electrons, their valence electrons are tightly connected to the atoms. So they cannot leave the atoms. They are tightly connected to the atoms. They cannot conduct current if they get heated or they get enough thermal energy, or if you apply to them electric field. This is why we use them as insulators to protect us from electric shocks, or to separate one signal, say in this wire, from the signal in that wire, because no current can go through these insulation materials. We use them very often in different types of applications. Capacitors, if you've seen how capacitor is being formed, a capacitor is really two metal plates, and between them you put some insulation material. And by changing the property of this insulation material, or by changing the spacing between these two metal electrodes here and here, or their area, you can get different values for that capacitance. The last type of material we are going to be using in this course, semiconductors. And semiconductors, they are somewhere in between conductors and insulators in their ability to conduct current. So for example, here's silicon. Silicon is one of the most important semiconductor materials. It has an atomic number of 14, so there are 14 protons in the nucleus, and the electrons are distributed over 3 shells, with the outermost shell containing 4 electrons. And we call these electrons, of course, the valence electrons. They are not really, they need a little bit of energy to leave the atom. But if you see how silicon forms itself as a material, you see that every silicon atom will share one of its electrons with another silicon atom, creating what we call here a covalent bond. So there's a covalent bond created between these two atoms. Each one of them is sharing 1 electrons. And you can see this one as well is sharing 1 electron with this atom, and so on. So this is called a covalent bond, the second covalent bond, a third, and a fourth. So this covalent bond is what keeps the silicon material together. And at room temperature, they do not conduct current. If you heat them, they can start, some of these covalent bonds can be broken, and these electrons become free, and then they start to conduct current. And I will show you later that there are another way to increase the conductivity or increase the number of electrons available for conduction is by adding impurities. And we'll talk about that in 2 weeks from now when we get to start the p-n junction part. Now I will move to a very important subject. And as I mentioned before, many even electrical engineers who analyze circuits do not keep this in their mind, that the origin of the currents and voltages and so on is nothing but electric field. So I will try to explain this to you in a very brief way. When we have electrons, when we have charges, positive charges or negative charges, positive charges, I will call them protons, negative charges are called electrons. And the electron is the smallest charge in this universe. It has a charge value of minus 1.6 times the minus 19 Coulomb. And when you put two charges at a distance between one another, they do affect one another with a force. The opposite charges, they are attracted, and similar charges, they repel one another. And this is according to a law called Coulomb's law. It's a very fundamental law in electromagnetics, but as you will see, it's really actually the basis or the basic concept in all circuit analysis. So keep in mind, when you have two charges, similar charges do repel. So two negative charges will repel against one another, two opposite charges, one positive and one negative, will attract to one another. This is according to Coulomb's law. So here we have a graphical illustration of Coulomb's law. Here you have two positive charges. They are located somewhere in the space. You see they are trying to push one another in the opposite direction. Positive charges, rule of nature, similar charges, rule of nature, they do rebel against one another. So this one will be affected by a force moving it in this direction. This one will be affected by a force of the same magnitude, but it's trying to move it in that direction. The same will happen when you have two negative charges. If you have these two negative charges, they are located somewhere in space. They are trying to push one another in the opposite direction. So this one will be affected by a force trying to move it this way. This one will be affected by a force trying to move it that way. So these two forces are equal in magnitudes and they are opposite in direction. If you have a positive charge and a negative charge as shown here, they try to attract one another. So each one of them will affect the other by a force. The positive charge is being pulled towards the negative charge, and the negative charge is being pulled towards the positive charge. So you can see this force is pointing from left to right. This force is pointing from right to left. So again, the two forces are equal in magnitude but opposite in direction. And mathematically, this is the expression for the force affecting the second charge due to the first charge. So if you have two charges, Q1 and Q2, this is the expression for the force affecting charge Q2 as a result of charge Q1. It's equal to some constant. It's called 1 over 4 by epsilon. And the epsilon is called the permittivity of the material. We don't have to worry about this for this course. It's simply, it's some electrical property of any material in the universe. Even our human tissues, they have their own epsilon. So this number for free space is nothing but 9 to the power multiplied by 10 to the power 9. So this is what we're going to be using it. This is the value of the first charge. This is the value of the second charge. This R12 is simply the distance between them. So the further the distance, the weaker the force. And you can see the distance is being raised to power 3. And the R12 is simply the unit vector point is a vector. So it's not a unit vector, it's a vector pointing from charge Q1 to charge Q2. And if you have studied this from your vector analysis, R12, which is a vector pointing from charge from point 1 to point 2, is equal to the position vector R2 minus the position vector R1. So if we know these charges, if we know their values, and if we know their location in the space, we can tell exactly what is the force between them. This is the force affecting the second charge due to the first charge. If you want to get the force affecting the first charge due to the second charge, you have to multiply this expression with a negative sign. So this is a very fundamental concept in electrical engineering, the concept of the electric force affecting two charges, whether they are similar charges or opposite charges. And if you see, if these two are opposite, you will see that the sign will take care of itself and you get the right direction of this force here. Okay, let's have an example. I know some of you are not familiar with this concept. Let's have an example. We have two charges. One of them is a negative charge. It has a value of minus 20 microcoulomb, so 20 10 to the minus 6 coulomb. Coulomb is the unit of the charge. It's located at the point minus 6, 4, and 7. So minus 6 in the x direction, 4 in the y direction, 7 in the z direction. And we have a second charge, QB. It has a value of 50 microcoulomb. So 50 10 to the minus 6 coulomb is located at the point 5, 8, and minus 2. We would like to find the vector force exerted on QA by QB. So we would like to know the force affecting QA as a result of the presence of QB. So notice this means that QE here plays the role of Q2 in the expression I have shown you earlier. So we know all the values that we need. We know what are the values of these two charges. They are both given QA and QB. We know their location in space. Then we can get the vector R12, which is pointing from point B to point A. It's really RBA, and the RBA is nothing but RA minus RB. And I am warning you here that I'm asking for the force affecting QA as a result of QB. So QA here plays the role of Q2 in the expression I've shown you in the previous slide. So now this is simply direct substitution in the law, very straightforward. Let's take a look at this derivation. So in examples like this, I know I'm not going to get deep into electromagnetics, but when you draw something like this, you have to draw your origin. So this is the origin. This is the position vector of the point A. This is RA. This is the position vector of the point B. It's pointing from the origin to point B. This is a vector I call RBA. It's a vector pointing from point B to point A. And the RBA from this figure is nothing but RA minus RB. And this is what I wrote here, so it's RA minus RB. This is the position vector of point A. This is the position vector of point B. And then when we subtract vectors, we subtract similar components. So minus 6 minus 5 gets minus 11. 4 minus 8, you get minus 4. 7 minus minus 2, you get 9. So this is the vector RBA. If you try to get the magnitude of this vector, which you can get by simply taking the square root of this, the square root of the sum of the squares of these components. It's going to be the square root of 121 plus 16 plus 81. You get that the distance between these two charges, this is the modulus of RBA. And I should correct myself here. This should be a vector, so I should have a line underneath this one. So this length here is 14.76 meters. Now we have all the things that we need to start calculating using Coulomb's law, the force affecting QA as a result of the charge QB. And remember, the force affecting QB as a result of the charge QA will be the opposite one. You simply multiply your answer with a negative sign. It is the same magnitude, but it's opposite direction. Okay, so now we substitute the Coulomb's law. This is the expression for Coulomb's law here. It's simply K, the constant, 9 10 to the minus 9, I mentioned to you about. QB, QA, the distance between them to the power 3. And this is a vector pointing from the point B to the point A. Because we now are trying to calculate the force affecting QA as a result of QB. We know all this, that this one is 20 microcoulomb, we bought that. This is 50 microcoulomb, we bought that. Distance is 14.76 to the power 3. We multiply all this by the vector RBA, which we calculated earlier. It's minus 11 in the x direction, minus 4 in the y direction, and 9 in the z direction. You multiply all this constant, determine this constant here, determine its value, and then you multiply by that vector, and then I expanded it here. So this is the x component, this is the y component, this is the z component. This is the force affecting the charge QA as a result of the charge QB. Of course, the other one, FAB, the result affecting the charge QB as a result of the charge QA is simply the opposite of this one. So it's minus 30 here, minus 11 here, and plus 25 here. It's going to be the negative sign.